So, announcements. The chapter, homework number 6 on chapter 7 is due on the 24th. I gave you an extension because of the outage on Monday. AWS broke, so Pearson broke, so you couldn't access your homework on Monday morning. Homework number 7 on chapter 8. Robinson? Okay. Homework number 7 on chapter 8 will be due on the 29th. Homework number 8 on chapter 9 is due on the 5th. Also, our review of chapters 7 through 9 will be on the 3rd. Our exam on chapters 7 through 9 will be on the 5th. So we're going to finish chapter 9. We'll have review and exam. And we have a lab today, which should hopefully be short. So chapter 9 is about linear momentum and collisions. So here is an example of conservation of linear momentum in a collision. Two things colliding with each other, and you can figure out their final velocity based on conservation of momentum. So we'll talk about what linear momentum is. We'll explain how it's derived from Newton's second law and how it ties to Newton's second law. It comes out of Newton's second law and Newton's third law. So if you combine the two of them, you get momentum. Then there's impulse and conservation of linear, and then we'll talk about conservation of linear momentum. And then inelastic collisions, elastic collisions, center of mass, and systems with changing mass, where we'll talk about rocket propulsion. So linear momentum is a vector quantity that's sort of a measure of how much inertia, it's sort of it's the idea of inertia combined with movement. So momentum, the momentum of some object is a vector quantity. Its mass times its velocity. So it's a vector. It'll be in the direction of the velocity, but it will be increased by the mass. By a factor of the mass. So if you have two objects traveling at the same velocity, the one with more mass will have more momentum. The momentum is a vector. Its direction is the same direction as velocity. So here are some examples. We have two objects of the same mass. And we want to talk about their change in momentum. Here we have this teddy bear. It goes from moving down with a velocity v to having 0 velocity. And then here we have a ball that bounces. It goes from going down with a velocity v to going up with a velocity v. In case A, we go from minus mv to 0. The change in momentum is mv. In case B, we go from minus mv to plus mv. The change in momentum is 2 mv. When you bounce something off of something, that's a bigger change in momentum. And because momentum is conserved, that means more momentum is transferred by bouncing something off. So if you're trying to move something by throwing things at it, if you throw things that bounce off, that'll be more effective than throwing things that stick. So momentum is mass times velocity. If you have a 72.3 kilogram jogger running with a speed of 1.13 meters per second in the positive x direction, what is the jogger's momentum vector? So this is fairly straightforward. Momentum is just mass times velocity. Our velocity is 3.31 meters per second in the x direction. Our mass is 72.3 kilograms. So our momentum is mass times velocity. Momentum is P. Don't ask me why. So 72.3 kilograms times 3.31 meters per second in the positive x direction gives us 226 kilogram meters per second in the positive x direction. Here we have the momentum of an airplane flying with a speed of 549 meters per second, has a magnitude of 3.93 times 10 to the 4 kilogram meters per second. What is the mass of the airplane? So our velocity is 54.9 meters per second. Our momentum is 3.93 times 10 to the 4 kilogram meters per second. So we're looking for mass. Momentum is mass times velocity. So the magnitude of momentum is mass times the magnitude of velocity. So mass is going to be momentum over velocity. So 3.93 times 10 to the 4 kilogram meters per second over 54.9 meters per second gives us a mass of 716 kilograms. So here we have a problem about the total momentum. We have three objects. We're interested in the total momentum. Total momentum is very important because total momentum of all objects is what is conserved. So at a city park, a person throws some bread into a duck pond. Two 4 kilogram ducks here and here, and a 9 kilogram goose here paddle rapidly towards the bread, as shown in our sketch. If the ducks swim at 1.1 meters per second and the goose swims with a speed of 1.3 meters per second, find the magnitude and direction of the total momentum of the three birds. So you'll be adding these three vectors up. Now, momentum is mass times velocity. Let's go over what we know. The mass of the ducks, 4 kilograms each. The mass of the goose is 9 kilograms. There are two ducks. There's duck 1 and duck 2. The velocity of duck 1 is 1.1 meters per second in the positive x direction. The velocity of duck 2 is minus 1.1 meters per second in the y direction. The velocity of the goose is 1.30 meters per second in the y direction. And we are looking for the total momentum. So we'll need to find the momentum of each duck and the goose and add them all together. So momentum is mass times velocity. So our total momentum is going to be momentum of duck 1 plus momentum of duck 2 plus momentum of the goose. So let's find each momentum. Momentum of duck 1 is mass of duck 1 times velocity of duck 1. So that's 4 kilograms times 1.1 meters per second in the positive x direction. That's 4.4 kilogram meters per second in the x direction. For duck 2, mass is 4 kilograms. Velocity is minus 1.1 meters per second in the y direction. So minus 4.4 kilogram meters per second in the y direction. And then for the goose, mass of the goose times velocity of the goose. The mass of the goose is 9 kilograms. The velocity of the goose is 1.3 meters per second in the y direction, positive. So that comes out to 11.7 kilogram meters per second. So our total is going to be 4.4 kilogram meters per second in the x direction, minus 4.4 kilogram meters per second in the y direction, plus 11.7 kilogram meters per second in the y direction. So if we combine our x's, we have 4.4 kilogram meters per second in the x direction, and then 11.7 minus 4.4 is 11.3 kilogram meters per second in the y direction. So if we want to find the magnitude, the square root of the x term plus the x term squared plus the y term squared comes out to 8.52 kilogram meters per second. And the angle is going to be the inverse tangent of the y over the x, so 7.3 over 4.4, which is 58.9 degrees. Any questions about this? Okay. So Newton's second law is force equals mass times acceleration. But this is only valid for objects with constant mass. It turns out we can rewrite this in a more general form that's also useful when the mass is changing. It turns out sum of all force equals change in momentum over change in time. Because momentum is mass over velocity. So mass times change in velocity over change in time gives you mass times acceleration. So that's momentum over change in time. Yeah, we have mass times acceleration. That's mass times delta V over delta T. So that's delta momentum over delta T. And I mean, strictly in calculus terms, what this is, sum of all force is d momentum dt. And these are vectors. So that you could rewrite Newton's second law that way. And this idea of force being momentum over time, well, we can rearrange this equation. We multiply both sides by delta t. You can get some interesting things, but that'll be the next section. So here we have, so if we rearrange both things by multiplying by delta t, we can get that sum of all force times delta t equals delta momentum. And that is a useful concept. So object 1 has a mass of 1 kilogram and it's acted on by a force of 100 newtons, while object 2 has a mass of 100 kilograms and it is also acted on by a force of 100 newtons. Is the change in momentum in 1 second greater for object 1, greater for object 2, or the same for both objects? And then is the change in velocity in 1 second greater for object 1, greater for object 2, or the same for both objects? Remember, force equals change in momentum over time. So force times time equals change in momentum. So is the change in momentum in 1 second for object 1 greater for object 1, greater for object 2, or the same for both objects? What do you think? They both have the same force on them, but they have different masses. There's two objects. One is 1 kilogram, one's 100 kilogram. Both of them are acted on by the same 100 Newton force. Is the change of momentum in 1 second greater for object 1, the 1 kilogram object greater for object 2, the 100 kilogram object, or the same for both objects? And then secondly, is the change in velocity in 1 second greater for object 1, greater for object 2, or the same for both objects? Oh, I forgot to do a write-up of this one. Okay. Well, I'll just explain it. So the change in momentum will be the same for both objects. Because the sum of all the forces equals change in momentum over change in t. So force times delta t equals delta momentum. Force is 100 newtons. Time is 1 second. That equals the change in momentum. That'll be the same for both objects. Same force, same time. But the change in velocity will be different, because this is what the 100 Newton seconds. That is equal to either 1 kilogram times delta V, where delta V will then be 100 meters per second, or, so this is object 1. And object 2 is 100 Newton seconds equals 100 kilograms times delta V. So delta V will equal 1 meter per second. So the change in momentum will be the same for both objects, but the change in velocity will be greater for the lighter object, object 1. So this force times delta t, we define this as impulse. Impulse is the average force times the time over which it's applied. And impulse is also equal to change in momentum. And this is impulse. The unit is Newton seconds, which is the same thing as kilogram meters per second. It's the same units as momentum. Impulse is a vector. It's in the same direction as the average force. So when you apply a force to an object, it gives that object an impulse, which will change its momentum. So we can rewrite force average as delta P over delta T. Force average equals delta P over delta T. Multiply both sides by delta T. We get force average times delta T equals delta P. So we see impulse equals change in momentum. The impulse is equal to the change in momentum. And because it's force times time, it's something that's relatively straightforward to calculate. And so you can time momentum to force very easily. So the same change in momentum can either be produced by a large force acting for a very short time, like hitting a ball with a bat, or a smaller force acting for a longer time, more like throwing a ball, because you're doing it over a much longer period of time than the actual point of impact with a bat. So here's a problem with a baseball. If you have a 0.144 kilogram baseball moving towards home plate with a speed of 43 meters per second, when it is bunted, hit softly. The bat exerts an average force of 6.5 times 10 to the third newtons on the ball for a time of 1.3 milliseconds. Remember, a millisecond is a thousandth of a second. The average force is directed towards the pitcher, which will take to be the positive x direction. So what is the final speed of the ball? So the ball starts with a speed of 43 meters per second in the negative x direction. It has a mass of 0.144 kilograms. There's a force on it of 6.5 times 10 to the third newtons over a time of 1.3 milliseconds. And you want to figure out the final speed of the ball. So you're going to do this by figuring out the change in momentum, the final momentum, and then the final velocity of the ball. So mass of the ball is 0.144 kilograms. The velocity of the ball is minus 43 meters per second in the x direction. The force on the ball is plus 6.5 times 10 to the third newtons in the x direction. The time is 1.3 milliseconds. We want to find the final velocity. So to do that, we're going to need to know the initial momentum, the final momentum, and the impulse, the change in momentum. So impulse is force times time. So 6.5 times 10 to the third newtons in the x direction times 1.3 times 10 to the minus third seconds gives us 8.45 Newton seconds. This is change in momentum. So the change in momentum is the final momentum minus the initial momentum. So that's mass times velocity minus mass times velocity initial. So mass times velocity is mass times velocity initial plus change in momentum. So velocity is going to be mass times velocity initial plus change in momentum all over mass. So 1.44 kilograms times minus 43 meters per second in the x direction plus 8.45 Newton seconds in the x direction divided by 1.44 kilograms. So the initial momentum is minus 6.19 Newton seconds. We add 8.45 Newton seconds, and then we'll divide by 1.44. So 2.26 Newton seconds divided by 1.44 kilograms gives us a velocity of 15.7 meters per second in the positive x direction. I forgot to copy over the x hat, but quickly type that in. Oh. Yeah. So here's a more conceptual problem. A person stands under an umbrella during a rain shower. A few minutes later, the raindrops turn to hail and bounce off the umbrella. So the number of drops hitting the umbrella per time remains the same, as does their speed and mass. Is the force required to hold the umbrella in the hail greater than, less than, or equal to the force required in the rain? And which of the following do you think is the best explanation for your prediction? Is it one, the force required is greater because the hail bounces off the umbrella, which causes a greater change in momentum and a greater impulse? Two, less force is required because the hail bounces off the umbrella and hence has little effect on it. In contrast, the raindrops hit the umbrella and come to rest. Or three, the force is the same in either case because the same amount mass of water, liquid or ice, hits the umbrella with the same speed. So which of these do you think is the correct answer? So who thinks the force required in this second case with the hail is greater? Who thinks less force is required because the hail bounces off the umbrella and thus interacts with it less? And who thinks the force is the same because the same amount of water hitting the umbrella with the same speed? Well, the people who said number one are correct. The force is greater because the hail bounces off the umbrella, which causes a greater change in momentum and a greater impulse. So when you're holding it up under the hail, you not only need to provide enough force to stop the water, you have to provide enough force to push it away, to bounce it off. So that's extra force required. So here we have a force, the measurement of a person's foot with the ground. So a force platform measures the horizontal force exerted by a person's foot on the ground. The sketch shows a force versus time data taken by a force platform for a 71 kilogram person who is jogging with increasing speed. The first part of the data from t equals 0 to 0.3 seconds indicates a negative force as the person's foot comes to rest. So this is, they're putting their foot down and their foot is slowing down. And then the second part of the data from 0.3 to 0.8 shows a positive force as the person pushes off against the ground to gain speed. And the impulse, so the impulse during the first part is negative 2.7 kilogram meters per second. The impulse during the second part is 26.2 kilogram meters per second. So for the time period from 0 to 0.8 seconds, what are the average horizontal force exerted on the jogger and the jogger's change in speed? So what do we know? We know the mass, 71 kilograms. We know impulse 1 is minus 2.7 kilogram meters per second. Impulse 2 is 26.2 kilogram meters per second. Our total time is 0.8 seconds. Our first question is we want to find our average force. And our second question is we want to find our change in velocity. To find change in velocity, we're going to need to know change in momentum. So both of these problems are going to use the total impulse. So for part A, the net impulse, the total impulse, is the average force times the time. So the net impulse is impulse 1 plus impulse 2. So it's minus 2.7 kilogram meters per second plus 26.2 kilogram meters per second, which is 23.5 kilogram meters per second. And the average force is going to be the net impulse divided by time. So 23.5 kilogram meters per second divided by 0.8 seconds. The average force is 29 newtons. The net impulse is also the change in momentum. The change in momentum is mass times the change in velocity. So the change in velocity will be the net impulse divided by the mass. So 23.5 kilogram meters per second divided by 71 kilograms, 0.33 meters per second. That'll be the change in velocity. So a steel ball and a rubber ball collide. Is the impulse received by the steel ball greater than, less than, or equal to the impulse received by the rubber ball? What do you think the case is? So who thinks the steel ball gets more impulse? Who thinks the rubber ball gets more impulse? Who thinks they both get the same amount of impulse? Well, I'll go through and explain. Their impulses will be equal in opposite directions. Newton's third law says force from object 1 equals minus force from object 2. Those forces are going to last for the same amount of time. So the impulse will be, impulse is force times delta t. Force 1 times delta t equals minus force 2 times delta t. Impulse 1 will equal minus impulse 2. So same magnitude, opposite direction. Now, because of this fact, that the impulse on two objects interacting is the same, then this leads to conservation of momentum. The net force acting on an object is the rate of change of its momentum. If the net force is 0, the momentum doesn't change. So if the net force acting on an object is 0, its momentum is conserved. Momentum final equals momentum initial. This works for a system. If the net external force on a system is 0, momentum of the system is conserved. So we can talk about internal versus external forces. Internal forces act between objects in the system. So if we add up all the internal forces of a system, they will always add up to 0 because they occur in action-reaction pairs because of Newton's third law. So as all pairs act between objects in the system, the internal forces always sum to 0. Therefore, the net force acting on a system is the sum of the external forces acting on it. And this got, let me just move that up a little. And so because of this, for a system of objects, if the net external force, so the internal forces can't change the momentum of a system. So internal forces have no effect on the net momentum of a system. So if the net external force acting on a system is zero, the net momentum is conserved. Thus, the sum of all the momentums before and after something will be equal. But the momentums of the components of the system may change. And the most common way to talk about this is in collisions, because we can go, collisions happen really fast. So because collisions happen really fast, we can ignore the external forces. We're only interested in the internal forces. So here's an example of internal forces moving the components of a system. The system itself starts with zero momentum, and after the two boats push apart with 46 newtons of force, it will still have zero momentum. So here's that problem. Two groups of canoeists meet in the middle of a lake. So as long as the external forces, if the sum of the external forces equals zero, the sum of all the momentums initial equals the sum of all momentums final. So two groups of canoeists meet in the middle of the lake. After a brief visit, person in canoe 1 pushes on canoe 2 with a force of 46 newtons to separate the canoes. If the mass of canoe 1 and its occupants is 130 kilograms, and the mass of canoe 2 and its occupants is 250 kilograms, find the momentum of each canoe after 1.2 seconds of pushing. I believe in your book, they actually use kinematics to figure this out, because this was actually a problem earlier, back in chapter 2, I think. No, 3, with Newton's third law. But here we can use momentum to do it, an impulse. So I'll go through that process. The mass 1 is 130 kilograms, mass 2 is 250. Force 1 is minus 46 newtons, force 2 is plus 46 newtons. The time is 1.2 seconds. The initial momentum is 0. And we're interested in momentum 1 and momentum 2. Impulse is force times time. So impulse 1 is force 1 times time. So that's minus 46 newtons times 1.2 seconds, or minus 55.2 newton seconds. That also equals change in momentum 1. So momentum 1 minus momentum 0 is 55.2 newton seconds. The momentum 1 minus 0 is minus 55.2 newton seconds. Momentum 1 will be 55 newton seconds. For momentum 2, impulse is 46 newtons times 1.2 seconds, or plus 55.2 newton seconds. Change in momentum 2 will be plus 55.2 newton seconds. And again, the change from 0 is positive 55.2 newton seconds. So momentum 2 is plus 55 newton seconds. So the total momentum is still 0. The final momentum of the two canoes and their occupants, the previous problem, is equal to the initial momentum. Is the final kinetic energy of the system greater than, less than, or equal to the initial kinetic energy? So remember what kinetic energy is, 1/2 mv squared. So in this case, is the final kinetic energy greater than, less than, or equal to the initial? So we have, so who thinks the final kinetic energy is greater than the initial kinetic energy? Who thinks the final kinetic energy is less than the initial kinetic energy? who thinks it is equal to the initial momentum? Well, you were correct. It is greater. Starts at 0, nothing's moving, and afterwards stuff is moving, so there is kinetic energy. So it goes from 0 to something. So it's greater than the initial kinetic energy. I can calculate it, but it's not worth it. So often in something like this, momentum may be conserved, but kinetic energy is not necessarily conserved. We can go a little bit longer. So let's talk about collisions. Inelastic collisions are collisions with two objects. Collision is when two objects strike one another. The time of a collision is short enough that external forces can be ignored. And the generalized definition of an inelastic collision is one in which momentum is conserved, but kinetic energy is not. We will be talking about completely inelastic collisions, because partially inelastic collisions are complicated and messy, and you need to add another factor to take into account how elastic they are. But completely inelastic collisions are when the two objects stick together afterwards. So they have different velocities before and the same velocity after. That is a completely inelastic collision. It will have the most loss of kinetic energy possible. So this is an example of a completely inelastic collision. We have two train cars. You have car 1 moving at with mass 1, moving at velocity 1 initial. Hits car 2 with mass 2, moving at velocity 2 initial, which is less. And then they couple. And now they are one big car with mass 1 plus mass 2, traveling at some velocity v final. Because they're coupled, they have to travel at the same velocity. So our initial momentum is mass 1, velocity 1 initial, plus mass 2, velocity 2 initial. Our final momentum is mass 1 plus mass 2 times final velocity. If you set these two equal to each other and solve for final velocity, you get mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial over mass 1 plus mass 2. So these are fairly straightforward to work out because they have this nice condition where the final velocity is the same for both. So a tool that exploits this is something called the ballistic pendulum. So if you know the initial velocity and the mass joins this larger mass that starts at rest, so you have some initial velocity, they combine into a mass m plus big M plus little m, and then it swings upwards to some height. The height can be found using conservation of mechanical energy after the object is embedded in the block. So that describes going forward, figuring out the height based on the initial velocity. More commonly, these are used the other way around. You shoot something into a mass, it swings up. You measure the height it swings up to. Use conservation of momentum to figure out how fast it was moving here. And conservation of energy to figure out how fast it was moving here. And conservation of momentum to figure out how fast the projectile was moving. So this is a way you can figure out how fast, like a bullet is. If you have collisions in 2 dimensions, you apply conservation of momentum in each axis independently. You do it separately along each axis. So here we have some velocity 1. We have car 1 going at velocity 1 at 16 meters per second. Another car going at 21 meters per second. Their combination is going to have an x component that is going to be the momentum of car 1 here, and a y component that's the momentum of car 2 here. So here, if you have a railroad car of mass m and speed v, collides and sticks to an identical railroad car that's initially at rest. After the collision, is the kinetic energy of the system 1/2, 1/3, or 1/4 of its initial kinetic energy? So remember, for inelastic collisions, completely inelastic collisions, you have mass 1, velocity 1 initial plus mass 2, velocity 2 initial equals mass 1 plus mass 2 times velocity 5. So let's work this out. Momentum initial equals momentum final. So mass times velocity plus 0, because the first car is moving as mass m and it's moving at speed v. The second car has mass m, but it's moving at speed 0. So its momentum is 0, equals mass plus mass, the two masses together, times v final. So mass times v equals 2 times mass times v final. So v final is going to be half of our initial velocity. So let's find our final kinetic energy. Our initial kinetic energy is 1/2 mv squared. Because we have a mass m moving at a velocity v squared, velocity v, it gets squared. And there's no kinetic energy from the car that's at rest. Our final kinetic energy, well, we have 1/2 times twice the mass moving at v final squared. So that's 1/2 times 2m times v over 2 squared. That's 1/4 mass times velocity squared, because this is a quarter, this is a half, which is 1/2 of, this is a quarter times 2 times a half. You get a quarter. This is 1/2 of the initial kinetic energy. So basically, because it's half the speed but double the mass, we get half. I circled the wrong thing. Well, let me fix that. The initial kinetic energy. Oops. I will re-upload these slides. Sorry about that. So the correct answer is 1/2. Here on a touchdown attempt, a 95-kilogram running back runs towards the end zone at 3.75 meters per second, and a 111-kilogram linebacker moving at 4.1 meters per second meets the runner in a head-on collision. If the two players stick together because they grabbed each other, what's their velocity immediately after the collision, and what are their initial and final kinetic energies of the system? So I'll give you guys a few minutes to work on that. So this is an inelastic collision. Mass 1 is 95 kilograms, mass 2 is 111 kilograms. The V1 initial is 3.75 meters per second. V2 initial is negative 4.1 meters per second. We want to find V final, and we want to find the initial kinetic energy and the final kinetic energy. So momentum initial equals momentum final. So mass 1, V1 initial, plus mass 2, V2 initial equals mass 1 times mass 2 times V final. So V final equals mass 1, V1 initial plus mass 2, V2 initial over mass 1 plus mass 2. So that's 95 kilograms times 3.75 meters per second plus 111 kilograms times minus 4.1 meters per second divided by 95 kilograms plus 111 kilograms. And when you work that all out, you get negative 0.48 meters per second. The kinetic energy initial is 1/2 mass 1 velocity 1 initial squared plus 1/2 mass 2 velocity initial 2 initial squared, which is 1/2 95 kilograms times 3.75 meters per second squared plus 1/2 111 kilograms times minus 4.1 meters per second squared, which comes out to 1600 joules. Both of these are positive. This minus sign goes away when it gets squared, as opposed to the momentum where this is negative. And the final momentum is 1/2 mass 1 plus mass 2 times the final squared. So 1/2 times 95 kilograms plus 111 kilograms times minus 4.8 meters per second quantity squared, which is 23.7 joules. So a lot of energy is lost. And that energy is converted into vibrations, and it all gets dumped into the football players. So here, in a ballistic pendulum, an object of mass m is fired with an initial speed v initial at the bob of a pendulum. The bob has a mass big M and is suspended by a rod of negligible mass. After the collision, the object and the block stick together and swing through an arc, eventually gaining a height h. So we want to find the height h in terms of little m, big M, initial velocity, and g. I'll just go through this derivation. And this will be the last thing we do today before the lab. So initial momentum equals final momentum. So m v initial plus 0 equals big M plus little m times v final. So v final is m v initial over big M plus little m. Initial energy here equals final energy. So 1/2 big M plus little m v final squared equals big M plus little m times gh. So h equals 1 over 2g v final squared. Just divided both sides by big M plus little m times g. So h equals 1 over 2g times m v initial over a big M plus little m squared. So that can be rewritten as h equals little m over big M plus little m quantity squared times v initial squared over 2g. And in general, you're actually more interested in going the other way around, where you know h and you're trying to find the initial. But that is just, let me do a quick calculation, do some quick algebra. You get the initial squared equals 2g times big M plus little m over little m squared times h. So yeah. So the initial will be the square root of 5. So that is all I want to do for today. then we can do our lab. Let me. Stop sharing. Meeting.